Okay, hello student. We are going to study on the analysis of statically indeterminate still rigid frames. This frame has the pin at A and also at B. So this structure gonna have two reactions at the A, that is going to be A sub y, and also we're going to have A sub x, and also at the C you're going to have C sub y, okay, and the C sub x. This frame going to have the unknown of 4, and this frame is one free body diagram with 3 equations of equilibrium. So this frame going to have the degree of indeterminacy of 1. And we're going to solve this by the method of consistent. And you may read from this, they're going to set the horizontal force at C as the redundant. So this C gonna set as the redundant of this structure, okay, and then basis on this, let's set this one. They set the C sub x as the redundant, as the redundant. Is the kind of redundant force is the extra force. If you determine the C sub x, and then you can find the C sub y, A sub x, and A sub y later. And now we're going to set the second one. We're going to set what to? We're going to set the compatibility. Okay, at what? At C, because they said C. That's C. In x axis, C sub x. And now you're going to what? To separate this beam, and then we're going to refer to by using the principle of superposition. Okay, and then we can separate the frame into two cases. And now we're going to this one. If we set C sub y as redundant, this one going to be the primary frame, and then we're going to plus this one by the one that subjected to what? When we change when we set the C sub x as the redundant, the pin here change to the roller here, okay, and then under the application of primary frame subjected to the applying loading, okay, that's going to deform in this way. Since this one change from the pin to the roller, due to we set this one as the redundant, so this frame will deform like this under the application of the given loading. And what they said this one gonna have the displacement at this point along this one. Let's call it, this one is point C, move to the C palm. So we set this one as delta C, and let's say delta C horizontal equal to 1.328. okay, and again at A we still have this pin, and now this is going to be the rigid joint, and this is going to be the roller, and this one gonna pass, this one already subjected to the apply force. This is going to the frame. Okay, subjected to the redundant C sub x. Okay, so this one gonna subjected to the C sub x, and C sub x is the unknown, right? So the C sub x also gonna take this one, move to this position, and then what we have is the deformation of this one. If this one move like this one gonna move like this, and this structure gonna have this kind of shape, because this one gonna take the right angle, and then the frame may assume to deform like this. What happened is the deformation here cannot compute directly because C sub x is unknown. So if we set C sub x equal to 1, okay, we can determine the deformation of this one by the deformation at point C due to the applied force at C. Okay, that is if x equal to 1. If the total of C sub x, so deformation over here gonna be equal to this. Now we set the compatibility at C in the x direction, and what we have is this one is what? Let's see, if we set this one is positive, the deformation here is 0. Okay, and then what you have is equal to the deformation at here is delta sub CH is in this direction, and also we going to plus this one with F sub CC and C sub X, and now we have this one for 1.328. So our C sub X is gonna equal to minus of 1.328 millimeter, and then divided by F sub CC. Yes, by F sub CC. This is going to be the compatibility condition at C in x direction. And if we consider this, what we are going to do is we're going to determine F sub CC. Okay, so the next step is step 3. We are going to determine this is so-called the force displacement relationships F sub CC. Okay, and by using what? By using is depend on what do you have. We have the unit load method or the method of virtual work, and we also have the Castiglione theorem, but most of the time we use the method of virtual work, or the thick name is the unit load method. And we can see now only this one, so we come to here. The method of virtual work said the external virtual work will equal to the internal virtual work. Okay, and I just like assign you to determine this delta sub CH if you like, whether it's going to be 1.328 or not. I also going to remark you when you do the calculation of this frame has unequal fractional rigidity. So you do the equation, you must be very careful on this. So only this, you're going to determine this. What happened is, what is going to be this external virtual work? When you like to determine the external of virtual work of this structure, you're going to determine what the direction you like to determine the deformation. So you like to determine the deformation or displacement at C in the CX direction. So the 1.0 assumed force is going to be there, 1.0. And this 1.0 assumed force is going to determine, it's going to multiply the F sub CC. Okay, the force times the displacement is the work. And this is assumed, so it is virtual work. Since it occurs external of the structure, so it said it external virtual work. And then it's going to equal to the internal virtual work. This 1.0 gonna produce the moment M. So the moment M due to the 1.0, the moment M gonna time the deformation that occur on this structure is the d theta. And you guys know that is d square v by dx square equal to m over ei. And this is going to be d of dv by dx. Okay, so this is going to be what? D theta by dx equal to m over ei. And d theta is m over ei dx. Now, it's going to be m over ei dx and the integration due to the uniform deformation of this frame, due to the continuous deformation of this frame. And now, for this is going to provide you with the M. However, the C sub x is unknown. We set C sub x equal to 1. If this C sub x equal to 1, the force applied to point C gonna be the same. So the capital M gonna change to small m. And then this equation gonna be integration of what? Of M and dx over ei. Okay, so now our problem reduced to determine what? Determine the moment that occur in this frame subjected to the redundancy sub x of 1.2. And now let us set the coordinate. Okay, so you set this, you do two things. One, you're going to set the coordinate. For this one, you're going to set x1 and x2. There's two. And you also need to set the direction of the moment M. Actually, it's capital M and small m, but this time we reduce to only small m. So what would you like to set for this one? You may set this one as the x1. This one is x1, and this one as the x2. Okay, so before we can determine the equation of the moment, we determine the moment equation of M. Okay, we do two setup of that. And now, what should we do? We must determine the reaction occur here. So now, before we can do other, we need to move this one a little bit, and then we set up this frame is 4 meter and 3 meter. So this one is 4 meter and this one is 3 meter. This one gonna be point A, B, and C. This one subjected to the force of 1.0. And now what we have is, if you take the moment here, you may see you will have what the reaction here in this direction. Since 1.0 gonna rotate clockwise, so this C sub y gonna rotate counterclockwise. And you also gonna have this one. This one is to the right, so this one A sub x gonna be to the left, and this one is upward, so this one A sub y gonna be downward. And now just know that this one is 4 meter, this one 4 meter, and this one 3 meter. You may do the summation. Let's put this one, the summation of the moment about A equal to 0. If you do this one, so the C sub x gonna time this one 4, sorry, C sub y 4 C sub y, and this one is going to be equal to 1 half the moment arm of this, of 1 time what? This is time 3. So your C sub y gonna be 3 over 4. Your C sub y gonna be 0.75. So this is 0.75. Okay. And next, what you may have is the summation of x sub x equal to 0. So A sub x equal to 1.0. And you also have summation of f sub y equal to 0. Your A sub y gonna be downward, okay, as positive. So your A sub y is gonna be 0.75. Okay, so that's all the reaction for this. And now you're gonna cut this one for x1 and this one for x2. So do the cut of that. That's one gonna cut over here, okay, for the x1. So we have this one 1.0. This is going to be 1.0. This is going to be 0.75, and this one up. We have this one for x1, and we also need to do another cut, this one, okay, and then you're gonna have this, okay, and the force here still the same, is going to be 1.0, and this is going to be 0.75, and do the cuts there of x2. Okay, this is going to be x2. Now you're going to set the direction of the moment m. What would you like to have? Let's set this one as the small m1. Okay, and may set this one for the small m2. And then you may use the summation of the moment over here equal to 0. So this one produce 0 moment, only one. This one gonna be 1 times x2. So we have 1, and then 10 times x1, this one. And for this one, you do it again for the summation of the moment equal to 0. Just take moment here. What we have is this one gonna rotate. This is plus, and this is also plus. And if you take this, you may see this one 0.7 gonna produce in the same direction at m2. This is gonna be x2. However, this one gonna take 3 meter and going to be in the opposite direction of m2. So this is gonna be 1. 1 time this one, 1 time this is 3 meter, right? So 1 time 3. And this one gonna rotate in the same direction as M2. When you move, this one is 0.75 and this is gonna be x2. Okay, that is gonna be the equation of M2. Now you put back into this, you have the equation for f sub cc is gonna be equal to, so this one, integration of what? Integration of this one square, and also the integration of this one square. So f sub cc is going to equal to integration. For this orange one, that means you're going to integrate to this column. So integrate from 0 to 3. Okay. And this one gonna be x1 times x1. You have the x1 square. And then it's going to be dx1 divided by, this is only ei. Okay. ei1. Okay. And this one, the next one, we go to plus integration. Now, you integration of the beam from B to C for the length of 4 meters. So you integrate this from 0 to 4. Now, you do the parenthesis. This is 3 minus 0.75 and x2. And this is going to be square. And then you're going to dx2 by what? This is 2ei1. So 2ei1. Okay. Now, this is going to be x square. And this is going to be, that's term m2 square. If you do the integration, you do it carefully. And you will get this one equal to, this term is going to be x1 by 3. Okay, x1 power 3 by 3 from 0 to 3. So this is going to be 3 power 3 by 3 is 27 by 3 is going to be 9 over ei. Okay. And you do this again. If you like, you may separate this by your integration. If you do it, you're going to get this one by plus this term going to provide 6 over ei1. Okay, this is going to be ei1. And the total of them going to be equal to 15 over ei1. And the direction is going to follow this 1.0 unit. So the direction is going to be in this direction. Now, to come back here. Over here is millimeter divided by this. So you got to go back. The EI is 60,000 kilonewton per square meter. So this one is equal to 15 divided by 60. Okay, and then this is 10 minus 3. So 15 divided by 60 is what? 15 by 0.25. And then 10 minus 3 and meter. And you don't want to have it in meter, right? You're going to have it in millimeter. So this one going to be 0.25 millimeter. And it's going to provide the direction in this direction. Now, you just put it back in the next step. So the next step for we find the redundant. We find the redundant and reactions. Now we plug it back to here. The C sub x gonna equal to minus 1.328 millimeter, and then it's divided by 0.250 millimeter, you get this one as the negative of 5.312. This is going to be minus 5.312 kilonewton. What we have is our C sub x is not in this direction. Okay, it's going to be in this, it's not going to be in this direction. The C sub x is going to be in the opposite direction of this. Okay, now this one, the C sub x, gonna equal to 5.312 kilonewton, and the direction is gonna be this one. Now we have this one, C sub x of 5.312 kilonewton, and now you can see, if you know this, you can determine what else, the reactions at different point. So now this is 4. Just put this one in 4. We're going to determine the reaction. 4 and 3. So this one is 4, and this one is going to be 3 centimeter. Do the scaling, okay? Just do everything with the proper scale and draw it nicely. So the force here gonna be 220. That is gonna be 20 kilonewton per meter. And now we have the applied force here. This is 5.312 kilonewton. And if you take the moment here again, you can see this one supposed to rotate this one. I believe our C sub y should be in this direction. This is going to be 4 meter. This is 3 meter. And also this is 5.312. So this one is the A sub x. Okay. And you also going to have this one for the A sub y. And now we do determine this. Let's start by do the summation of the moment about A, B, C. About A equal to 0. And you can see the C sub y gonna time this distance. You're going to have C sub y and then time 4 C sub y here, and it's going to be in this plus directions. And this one also time 3 meter. Okay, this one gonna be in the same direction as C sub y plus 5.312, and then you time is by 3. Now you have this uniformly distributed load. Okay, and then it's going to rotate in the opposite direction, so it's equal to, this is going to be 20 times 4, so this is 20 times 4, that is going to be 80. Okay, and then the 80 is going to have the line of action here, so the distance here to here is going to be 2 meters. Now you have the C sub y. If you do it carefully, C sub y going to be 36.02. The C sub y is going to be 36.02 kilonewton. Okay, this is going to be 36.02 kilonewton. And now, if you do the summation of x sub x equal to 0, and this is positive, your A sub x is going to be equal to 5.312 kilonewton. Okay, this is 5.312 kilonewton. And the last one, summation of f sub y equal to 0. You put this one upward, positive. So your A sub y gonna be, A sub y is up. This one up, okay, plus 36.02, and that is gonna equal to up. This one is downward equal to 80, and then you may have your A sub y equal to 43.98 kilonewton. Okay, that's all we have for the reaction. And now the 5 step, you will draw the shear diagram, moment diagram, okay, and elastic curve. Okay, that is going to be the next step. But before you can do that, we're going to separate the beam and the column. Okay, the column here is going to be 3 meters. And then you may project it to this direction to draw the shear diagram and the moment diagram. And also in this direction you may have 4 meters, right? So this is gonna be 4 meters. And then this is going to have the uniformly distributed load of 20 kilonewton per meter. This is 4 meters. This is 3 meters. Now, you may elast this a little bit to provide the area for this. Okay, now what we have is the reaction. We have A sub x of 5.312 kilonewton and A sub y with 43.98 kilonewton. And this way you have this one of 36.02 kilonewton, and this one is 53.12 kilonewton. Okay, from these two segments of the frame, you may see which one you're going to determine the end shear and end moment here. Also, the end shear and the end moment here. Now, which part is going to be easier? I believe this one going to be easier than this one. Okay, because this have the uniformly distributed load. If you prefer, you may do this one easily. This is going to be 43.98 kilonewton, and this one will produce 5.312 kilonewton. And due to this is going to have the moment applied here. If you take the moment over here, you can see this one gonna rotate in this direction. So the moment here gonna be in this direction, and you may call this one as the M sub B. Okay, so the summation of the moment at this is A, this is B, at B equal to 0. This is M sub B. M sub B will equal to, this is 5.312, and time 3 meters. So your M sub B gonna be 15 point what? 15.94 kilonewton meter. And if you prefer, you have the joint B here, and you may know that since the joint B have no applied force, you may transfer this one directly into this, or you may transfer this one into the joint first. It's up to you. This is going to be the moment. This is going to be the upward force. This is going to be the horizontal force. This horizontal force is 5.312, right? It's 5.312 is going to be this one, and this one gonna be the 5.312 kilonewton. If you like, it can be transferred here to here directly if you like. This one down, this one up. Okay, so this one gonna be down, and this one gonna be up. Okay, this is gonna be 43.98 kilonewton. And the moment here applied to here is going to have the moment here and also have the moment here of 15.94 kilonewton meter. Okay, you know this load and force, this force and moment transfer, right? When there is no applied force at B, you can transfer directly from the NB to this NB, and this is C. Now, we're going to draw the moment diagram, and if you like, you may come this way for the column, and you may have this one for the X, this one X meter, this is 0, this is 3, and you may have this one for 3 kilonewton. Now, what we have is you move from the point of A here to the B, you get what? 0.53. That is 0.53. Let's say 0.53 is about 5 millimeter. So this one is downward minus 5.312 kilonewton, and W here is 0, so dV by dx equal to 0, so this is constant, and this is 5.312. Just close this one. This one is minus 5.312 kilonewton, and if you prefer, just put this one for the slope. Okay, that is for the shear, that is negative. And for the moment, you have this one again. This one is X meter. And this one, the A, since there is no external moment, this is going to be 0 kilonewton meter. And if you prefer, this is going to be M kilonewton meter. What we have is the shear is minus 5.312, so the dm by dx is going to be minus 5.312. Okay, and you see, since one this is minus, so it's going to be minus, 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 and over here is 15.94, and also if you do the sign convention of m, this m plus 15.94 equal to 0, so m is going to be minus 15.94. Okay, this is going to be about 1.5 centimeter. So we have this one for minus 15.94 on this. However, the slope going to be minus 0.312, minus 0.312, and minus 0.312 here. And then what we have is this moment going to close this one. Clockwise is going to be positive. Okay. And now we move to this one. This one is negative, and this one going to be negative. When this one is negative, it's going to defect like this. And then we have for the beam BC, the beam BC. For the beam BC, we have for the shear, it's here. This is up for 43.98. That's quite a lot, right? If you scaling That's going to be a lot of shear force compared to this one. Let's do another scale. Another scale. Let's put this one 20 for 1 centimeter. That is still a lot. This is going to be 40. Okay, let's see. 40. This is going to be the shear kilonewton. And this one x meter. What we have is about 40 kilonewton for 10 millimeter. So this is a little bit larger than 10 millimeter. And we have this one 43.98 plus 43.98. And then W is 20, so the dV by dx gonna be minus 20. And you know this is going to be 36. And this 36 gonna close this one. This is going to be 36.02. So this is going to be minus 36.02. And if you don't believe this one will be sub c minus 43.98, and it's going to equal to the minus of this area. It's going to be minus 80. So v sub c going to be minus 80 plus 43.98, and your v sub c going to be minus 36.02, and your graph is going to be this one, and this is going to be 0, and you can determine x, right? This is 43.98 divided by x equal to 20. So your x is going to be 43.98 divided by 20. How much it is? It's going to be 2.2 meter. Okay. And then we can go further to draw the moment diagram of this one. Let's more this one here for the moment. And this one is going to be the m kilonewton meter, and we have this one and this one. Okay, now what we have is this one, the rotation of the sine convention m plus 19.94 is 0. For this one going to be minus 15.94. Minus 15.94. So let's say it's maybe a scale about half of that, about 8 millimeter. We have 20 kilonewton meter equal to 10 millimeter. So the 15.94 about 8 millimeter. Okay, this is minus 15.94. And then you have 43.98. So the slope here, the dm by dx is going to be 43.98. Sorry, 98. And now the slope gonna reduce until here. The slope is gonna be 0. Okay. And the m here we don't know yet. The m here, minus 15.94, and that's one gonna equal to this area. Okay, it's going to be equal to the area of here. When you draw the moment, you got to check the shear diagram. So that is going to be 1/2 of 2.2, and then 43.98 times 43.98. You do the calculation, and then you may get your m equal to 34. M here minus of the minus, this one minus of the minus, this is minus, that's m here gonna be this one minus this one, 32.44 kilonewton meter. And then by doing this, this is going to be about 16 millimeter. This is 32.44 okay kilonewton meter, and dm by dx equal to 0, and your graph is going to be something like this. Okay, and then at this point is 0 kilonewton meter, you know that, right? And the slope here going to be what? The dm by dx is going to equal to minus 36.02. Okay, and then you have this one like this. You can check. This is going to be plus, going to be this one, and this one going to be minus. Now, your what? Your frame. You may draw it later here. 4 meter and 3 meter. So this one is 4 meter. 1, 2, 3, 4. And this one is 3 meter. And this is pin, and this is pin subjected to uniformly distributed load here and here, 20 kilonewton per meter, 20 kilonewton per meter. And you have this one is here, this is rigid joist, this is the point of inflection point. Okay, inflection point is about here, so this is going to be something like this. So this is concave upward, like this, and this is concave downward. Okay, and this is what? This is going to be taking care of the right angle, and this one going to rotate this way. So this is A, B, C, and what you may have is this one is going to be zeta sub B. This one gonna be zeta sub A, and this one gonna be zeta sub C, in which delta CH equal to delta CV equal to 0. And this one, delta AH equal to delta AV equal to 0. And due to infinity small or no axial deformation of the column and beam. So we have what? Delta BH equal to delta B phi equal to 0. So we have only 3 slope left for you to determine if you like to find it. And later, if you do this, we may put 1, 2, 3, 4. If this is the reinforced concrete structure, again, we also can put the reinforcement into our frame. Okay, and you may see this one for the extra reinforcement. You may put this one to this one up into this is going to be the IP or inflection point. Okay, and it's going to be, let's say, this one. This is also the same thing. And this one going to put on the top. And since the moment here is like this, so the reinforcement here also be like this. So that's some kind of extra reinforcement that we may have, including with the typical reinforcement that we have for the column and the beam. Okay, that is for the elastic curve. And this is for the reinforcement. Okay, that is what we have for this problem. We can solve this one easier because this problem they provide with some deformation. So our indeterminate frame, okay, when they select the C sub x as the redundance, the pin here change to the roller here. So under the application of the force that act on the primary frame, there is some deformation occur along the horizontal direction, and the set is for 1.38. Okay, and this frame will be plus this frame when it's subjected to the redundant force of C sub x. Okay, and since C sub x is unknown, usually we set C sub x equal to 1 and determine the deflection in this direction, and we call this F sub cc. And now if we like to determine the total of this, so we got to times F sub cc by C sub x, and then from this deformation you may set the compatibility condition or equation at c in x direction 0 equal to this one plus this one, and then you get the compatibility equation. When you find F sub cc, as you may determine this, okay, you can plug it back and then plug this one back, and then you get this redundant force. If this is in negative, so what they said due to this one will be incorrect. The direction reverse to this one. Now you can do the free body diagram, find the reaction. Also use the graphical method to draw the shear diagram and bending moment diagram, draw the elastic curve, put some reinforcement. Okay, you guys, you need to do some more practice by your own on this kind of problem, and I don't think this is hard. Okay, just require more practice. Okay, please enjoy this. This is the end of this clip.